and I'm going to go ahead and turn on the other recorder. And I should have everything posted up today as far as previous stuff. So, all right, there's that. And I'm going to go ahead and start sharing. And everybody should see the little girl with the cat. You've seen her all semester. She's grown a foot since we first met. I swear to God she has. So, all right, so let's go ahead and open up our white screen. All right, so we had some trends. Okay, we're talking colligative properties and things affecting different things, and we had some trends. And the first one that we saw was solubility with temperature. And as temperature goes up, solubility goes up. And a good example would be, say, glucose. All right, solubility goes up with temperature, and that is solids in water. And that's really what we're interested in mostly with this chapter is solid is just water. Okay, how do things dissolve in water? What happens in water? Things like that. Now, when we had gas in water, we found it went in the other direction. So we had, say, N2 and maybe methane. And once again, we're talking grams per 100 milliliters. And as temperature increases, solubility goes down. All right, and there's all sorts of equations out there that we can use. We're not going to use any, but there are equations that will describe this sort of thing. And then the final property that I want to give you before we actually get into calculations is solubility of gas versus pressure. Now, it turns out that the solubility of gas with pressure goes up. As we increase pressure. So many atmospheres, so many millimeters mercury. Now, there are lots of practical implications to these different properties, these different trends, and I covered, the implications of solid and water, and covered the implications of gas and water with temperature. But pressure is very interesting because if you happen to like soda, and I do not, you have inside of a soda can, you have what's called headspace. And in this headspace, you have gas. If it isn't a liquid or a solid, it must be a gas. Okay, so you have gas that's in the headspace. And what you have in the headspace is actually CO2. And what they do when they manufacture soda is that they put a certain amount of pressure of CO2 in there. What happens if you push on something? Well, generally, if you push hard enough on something, it should make sense that it will actually push into the solution. Okay, so as you're pushing harder and harder with that CO2, you're putting more and more carbon dioxide into the soda. Well, guess what CO2 does? CO2 gives you the fizz. All right. And it's not very popular around here, but if you go to Europe, when you ask for water at a restaurant, they'll ask you whether you want still or sparkling, because apparently over in Europe, they like sparkling water, which is water that has a lot of CO2 in it. I never knew this. First time I went to Europe, that's what they asked me, and I said, "What do you mean?" They said, "Do you want it with bubbles or not?" Of course, I was an American. That's why they said, "Yeah, what do you mean?" But that's how it works. Now, it turns out that the spritziness of whether you have soda, beer, or champagne depends on how much CO2 is dissolved in there, and it's actually controlled by the pressure. So it turns out that for soda, it's about 12 pounds per square inch. and you get up to, say, really spritzy beer, and it's about 14 psi. And you get in the champagnes, and it's about 16 pounds per square inch. So if you actually took a soda can and put a gauge on the top of it, it would actually read probably around 14 psi, pounds per square inch. I know that's not SI, but we're Americans, so we're going to use American units, and it would actually read about 14 psi. Now, I wish we were in class, and by the way, I really miss the in-person sort of stuff, but it is what it is, okay? So I would ask this question in class, and I would always get these confused and horrified expressions, which I can't see, unfortunately, because most of you have your cameras turned off. I love seeing the horrified expressions. And so you take this can and you shake it. All right. So I'm going to take this can of well, let's make it beer. Okay, because what's better than handing your buddy a can of beer freshly shaked? There's nothing better in the world, right? Okay, so I'm going to ask everyone, type in the chat box. It'll be your last opportunity. Well, I mean, your next to the last opportunity to type something in the chat box. So let me ask you, what do you think? What happens to the pressure? Will it go up? Will it go down? Or stay the same? What do you think? Just out of curiosity, just type it in the chat box. You can say goes up, you can say plus, you can say minus, and Crystal is emphatically saying, Mr. Pierce, I've got this. Pressure goes up. That's what Crystal says. She's not going to type it in the chat box, but I'm going to rat you out because you're trying to tell me. Okay? What do you think? What do you think, Justin? Is it going to go up or is it going to go down? Or is it going to stay the same? We shake that can of beer. And Justin says the same. That's interesting. I'm always interested in why people say what they say. And Crystal's going like, I don't know about this Justin guy, but okay. All right. So Justin, enlighten me. Why do you think it stays the same?
I have no idea. It probably goes up.
It's
I
just
don't
a
know.
guess.
Yeah, I think it goes up, but the way you're making a big to do about it, I want to say it's the same. I think it goes up.
You think it goes up, huh?
It
Okay.
explodes.
And it explodes, huh? Well, I want to see that. I really do, because as much as I shake this can, I've never seen one actually explode. Now, what I've seen though is pop the top. What happens? Comes flying out, right? Okay, because I know that's what you're thinking. I know that's what you're thinking. You're thinking it goes up. But Mr. Pierce, he's a sneaky professor, and he's going to show us something that is contrary to what we would think. And you're absolutely right. I am a sneaky professor, and it is contrary to what you think. Here's what's going on. I'm going to educate y'all today. All right? When you shake up that can, all right, believe it or not, the pressure doesn't change. You can prove it. You can put a pressure gauge on it. The pressure doesn't change. And so the question is what the heck's going on here? Because we're sciencey sort of people, or at least we're supposed to be, right? What's going on? What's going on here? Well, we got 14 pounds per square inch, and I just said pressure does not change. So what the heck's going on that makes it burst and foam and all over the place? Well, what happens when you shake this thing? What do you think is going to happen? Well, nothing's happening to the pressure. Okay, so we're not dissolving more carbon dioxide or anything like that. Okay, because if you dissolve more carbon dioxide, that would mean that carbon dioxide would have to go in, and so the pressure would have to go down. Well, first off, that ain't what's happening. If you're dissolving more CO2, pressure has to go down. Now, we already know that's not the case. You'll have to take my word for it, but pressure doesn't change. So what does happen? Let me draw a little picture here. I'm going to put little bubbles. You ever looked at a glass, and do you ever see like little bubbles on the inside? Well, yeah, this is what happens. You get little bubbles on the inside of things. So if you shake up this can of beer that you're handing to your buddy, guess what you get? You get a lot of bubbles. And you may say to yourself, well, what does that matter? Well, if you suddenly open that can, all right, bush, there it goes, right? Well, what's going to happen to these bubbles? All right, go back to the get. Now, this is where it's tying into chemistry. Okay, look, go back to the gas chapter. What happens to volume with decreasing pressure? It goes from 14 psi above atmospheric to atmospheric. So what happens to the volume of gases? Not changing the temperature, but what happens to the volume? If all of a sudden, whoops, let me change that 2 to a 1. If all of a sudden this becomes small, what happens to your fraction if the bottom gets small? If the bottom gets small, then the fraction gets bigger. As pressure goes down, volume goes up. So what happens to the volume of these bubbles? All of a sudden, these bubbles get very big. What's going to happen to a big bubble? Is it going to stick on the side of the can? It's going to go straight up as foam. And out the top it goes. And here you are. Ha! And here's your friend over here. And of course, he's wet with beer all over him. Okay? But you just use physics on him, physics and chemistry. Okay? As you release the pressure, the bubbles get big. If the bubbles get big, they're going to go out the top. They're going to go out the top. They're going to be foam. Okay? Which brings up the question. So you're at a party, and your friend who has seen this before, I know what you're going to do. He has seen this before, but he's been in Mr. Pierce's chemistry class, so he knows how to fix this. What do you do? What do you do to that can? Someone hands you a can. You ever seen anybody do this? They go, I've got you. And we'll turn that frown into a smile. What do they do with that can? They tap on it. Tap, 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 tap. You ever seen anybody do that? They take a can and they just tap on it, right? You ever wondered why they're tapping on it? Now, fun party trick. Go up to that person and say, so why are you tapping on that can? And they will give you all sorts of explanations. And by the way, you'll never get invited to another party again. Okay, don't ask science questions at parties. Pro tip, been there. All right. So what are they really doing? Tap, tap, tap. What do you think they're doing? They're knocking those little bubbles off, aren't they? And when you knock off the bubbles and there's no bubbles and you open it up, psh, no problems. You can do this yourself. This is an experiment that you can try yourself. Take a can of beer, can of Coke, whatever. Shake the heck out of it. Set it down. Tap, 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 tap. Open it up. You will see for yourself. No more gushing coming out the top. No more. You'll see for yourself. You should try this. I've actually done that experiment just to see for myself. And sure enough, you really have to be pretty aggressive with the tapping. You do have to be pretty aggressive, but if you tap enough, you can safely open that can no matter how much you shake it. So what's going on here? We got gas laws. It's gas laws. All right? The other thing that's going on here is that the solubility of gases depends on the pressure. If you shake that can, you're not changing the pressure. So what happened to the solubility? The solubility is the same. So you have to look at something else. What's that something else that's going on? Hey, you created a bunch of bubbles. Sometimes the explanation is not nearly as sciencey as you would think. All right. Sometimes it's not nearly, but you have to look a little deeper sometimes. Okay. So now you know I have ruined you for your life. Every time you go to a party and someone shakes up a can and hands it to someone, you will say, but wait, 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 wait. What do you think? Does the pressure go up? And then you'll never get invited back again. So, and I've been guilty of that. All right. So, solubility of gases depends on the pressure. Okay. And if you're not changing the pressure, you're not changing how much is dissolved, even if you shake it. All right. You're not changing the solubility of the gas. All you're doing is creating bubbles. Okay. So that's what's going on there. Okay. So we have our three trends. We have solids and water with temperature, generally goes up. We have gases and water with temperature, generally goes down. And we have gas versus pressure. The higher you crank up the pressure, the higher the solubility, the greater the spritziness or the fizz that you're going to get. Okay? All right, so we have those. Now we have to get on to colligative properties here. All right, let me do another slide here. All right, colligative properties. And we're going to do some, this is our last calculations for the semester. It's colligative properties. Yay, we're actually going to be done. I get to see my birdies fly away. My birdies fly away. But as I tell my wife, you know what I tell my wife? Sometimes my birdies get eaten by the cat. Most of them fly away. So don't be the one that gets eaten by my cat. All right. So take test 4 in the final seriously, for next week. All right. Nobody gets eaten by the cat. Not this time around. All right. But it happens. That's what cats are for. All right. So colligative properties. All right. First off, colligative, all it means is collection. All right. And it means it depends on however much you have. That's what colligative properties really means. It means collection. And so how many particles? Now, doesn't matter what the particles are. That's the beauty of colligative properties. It doesn't matter whether it's sucrose or glucose or sodium chloride or sodium nitrate or whatever. It doesn't matter what the particle is. It doesn't matter what the molecule is. What matters is how many do you have? Okay. And so there are several colligative properties, and I will list them out, and then we're going to do the calculations for them. Okay. So we have boiling point elevation. We have freezing point depression. We have vapor pressure. And we have osmosis, which I don't have an abbreviation for that. So I'll say osmosis means osmosis. Okay. I guess I could have said OS, but that just doesn't seem right. Okay. Because if you look in tables, usually it says BP, FP, VP. Okay. And so each one of these has its own equation that goes with it. So we're back to what I said before. We're in the plug and chug phase, which is you have an equation, you plug in the numbers, you chug away. All right, you go done. Okay. And so the one thing to keep in mind here, though, and this is where people mess this up all the time, boiling point, you're going to have an increase in the temperature. That's what it means to be elevation. Freezing point, you're going to lower the freezing point. Okay, it doesn't go the other way. So if we're going to make an error, usually errors are sign related. which means plus or minus, right? That's what we mean by sign, right? So when you do these calculations, you're calculating a correction. In other words, you have the temperature when it's pure, and then you calculate a number that you're either going to add or subtract. Okay, you have a choice. You can calculate the number, but you have a choice. Do you add or subtract? And I'll tell you, if it's boiling point, you're going to add because that's elevation. And if it's freezing point, you're going to subtract it off. Now, the equations do have a plus and minus sign, but it's easy to miss that, is what I'm saying. It's easy to miss the plus or minus part. If you get an answer that's lower than the original boiling point, well, and you made a sign error. Just change the sign, re-add it, okay? Because it's not going to be 100 degrees Celsius it's for water. It's going to be 101.2. It's going to be more than 100 degrees Celsius. Same thing to freezing point. Freezing point of water is what? Pure water is 0 degrees Celsius. It's not going to be 1 or 2 or 3 degrees. It's going to be -1 or -2.2. You see what I'm saying? Keep that sign in mind. Okay, we're going to keep that sign in mind. All right, so let me turn to the appropriate page so I can get the appropriate numbers, because everything is in a table. But you have to know what you have to do with the table. So let's calculate some things. And so let me pull up the and so what do we have here? We have some sort of K times some sort of molarity. So it's K times molality. And you're also going to have something called an I. Okay. Now, let's start with just freezing point. Okay, because that's the order it goes. This you look up. All right. M is something called the molality, which sounds unfortunately, it sounds a whole lot like molarity, but it's molality. Okay. And molality is moles per kilogram of solvent. All right. Now, and it gets a little m. Now, this is different from what we've done, several weeks ago when we had big M. See, that's so unfortunate. Not only do they sound very similar, but they both use M. Get little m, big M. Big M was moles per liter of solution. All right, this is moles per kilogram of solvent, whatever you happen to be dissolving it in. All right. All right. Now, before I get back to, freezing point depression, all right, what's going on with molality versus molarity? Okay. See, molarity is used because it's very easy to measure out the volume. You just take your solution, you pour it into a graduated cylinder, voila, you got the volume in milliliters, and milliliters times molarity gets you millimoles, which you can use in your calculations, right? The problem with molarity is it changes with temperature. Now remember, let's say we cool this down. We're not going to change the number of moles. That's however much is there. Whatever you got is whatever you got. Well, what about the volume? As we cool something down, what do you think happens to the volume of most things? Gets smaller. Most things shrink when they get colder. Most things expand when they get hotter. So if you make up a molarity solution at room temperature, if you use it on a hot day outside, well, the molarity is going to be different. Now, and you may say to yourself, well, why in the world would you use molarity anyway if that was the case? Well, you know what? Us sciencey sort of people, guess what we really like on hot days? Air conditioning. As long as your lab is air conditioned, your temperature stays constant. If your temperature stays constant, then the volume is going to stay constant. So whatever molarity you mixed up is going to be constant. As long as you're working in an air conditioned lab. Now, what about little m? Now, little m, on the other hand, do you see a volume measurement in there? And the answer is no, I don't see a volume measurement. You weigh out so many grams of whatever it is that you're trying to dissolve, you get the moles, you have so many kilograms of something you're trying to dissolve in. Well, you weigh that out too. Neither one of those are temperature dependent. What is temperature dependent is going to end up being the density. Okay. So we have molality now, which is temperature independent. And it also turns out that it depends on some constant times something called an I. Now, roundabout, all right, we're back here. We got the molality, which we will calculate in a minute. And we have K, which we're going to look up. Now, what about this I? This I is called the Van Hoff factor. All right, that's called the Van Hoff factor. Now, remember what I said. Colligative properties depend on the number of particles. Okay? So when we're calculating up molality, which is moles per kilogram, we're assuming that whatever we put in there is whatever we put in there. If I got a molar mass of such and such, and I got so many grams, I can tell you all day long how many moles I have, right? You got the molar mass, you have the grams. You should be able to do this. But remember, it's the number of particles. So Van Hoff says, how many particles? That's what Van Hoff says. So if I have sodium chloride, just regular old salt, and I dissolve it in water, what's going to happen? You're going to get a sodium plus, aqueous, and a chloride minus, aqueous. We now have how many particles? We have 2. So in an ideal world, the Van Hoff number for sodium chloride should be 2 in an ideal world. And we can do the same thing with, say, calcium chloride. Well, what's going to happen here? And please don't make me cry, because it is calcium 2 plus, okay? And it's not Cl2 minus, it's what? It's 2 chlorines. So how many particles do you have here? You have 3. And we can do this for, say, sodium sulfate and, you know, calcium phosphate or whatever. When they dissolve in water, they're going to produce ions. All right. Now, in an ideal situation, this would be your I for sodium chloride. And this would be your I for calcium chloride in an ideal world. Now, we don't live in an ideal world. We live in an imperfect world with imperfect things. And so your I is always going to be, it's going to be less than the 2. It's going to be less than the 3. Okay. This I is only true for very dilute solutions. Only true for very dilute solutions. Now, what do I mean by that? When these guys dissolve, they produce sodium ions and chloride ions. When calcium chloride dissolves, it produces calcium ion and chloride ions. This is true. But what's also true is there always some portion going back. So even though it's dissolved, they'll find each other, and momentarily it'll be a sodium chloride again, and it'll come apart. The calcium chloride, same way. They're drifting around. There's the calcium ion, two chloride ions, and momentarily they'll find each other. And the only way to make sure they don't find each other is to be very dilute. And so they're so far apart they never find each other. But if you have real solutions, then some of them are going to find each other at some point or another, and they're going to come back together. But as soon as they come back together, come apart. So at any moment, this I is some number less than 2. It might be 1.8. It might be 1.9. It might be 1.2, but it's some number less than 2. Okay, now, where do you find this number? Guess what? You look it up. Okay, so if you're working in a situation where you have to know what's the actual ion concentration, you'll have to make that correction. Now, what do we generally do? What I generally do is I go ahead and do this part, and then I do this last. Is generally what I do. Okay, so I'll go ahead and calculate what Kf is for every mole, and then I'll multiply times 2 or multiply times 3 or multiply times whatever I need to get the actual number. So let's do some of those. So let's calculate the freezing point depression. Okay, we're gonna, and this is from a practical standpoint. Have you ever seen ice on the sidewalk? I know it's hard to remember when it's 105 outside. It's hard to remember that at one point there was ice on the sidewalk. And so what do? You put de-icer down. But what they're really doing is you're putting salt down, and the salt lowers the freezing point depression, to a point where it's below the current freezing point, below the current temperature. So if you have the freezing point below the current temperature, guess what? It turns into liquid brine solution is what happens. Okay, so that's how your de-icer works. You have to put down a fair amount, actually. And so let's say that I mix, let's say 49.2 grams of sodium chloride, and let's say, I don't know, let's make this a fairly stout solution. Let's say 351 grams of water. What's the new freezing point? FP, which, by the way, is the same as the melting point. Melting point, freezing point, same thing. It really is. Freezing just means you're going from hot to cold, and melting just means you're going from cold to hot. But the freezing point, melting point is the same. So what's the new freezing point? And the freezing point of water, what's the freezing point of water? It's 0.00 degrees Celsius if it's pure. And notice that I have to put in the qualifier now, because we're in a chapter where we actually have to think about these things. Because, prior to this, I had said, oh, yeah, freezing point of water is 0 degrees Celsius, and I'll just leave it at that. Now we have to say freezing point of water that's pure is 0 degrees Celsius. Okay, it's got to be pure. Pure means there's nothing else in there. Well, we just mixed almost 50 grams of sodium chloride in there. It's not pure anymore. So, first off, before you do any calculations, our answer must be what? Less than 0 degrees Celsius. Why do I know it has to be less than 0 degrees? Because it's called the depression. When you're depressed, you don't feel happy, right? It's a depression. It's a freezing point depression. All right. We're looking for the new freezing point. We know it's going to have to be less than 0. That's to help keep us from making sign errors. All right. Well, the calculation itself is actually pretty straightforward. First off, we look at sodium chloride, and what do we see? Sodium chloride goes to sodium plus chloride minus, and that gives me an I equal to 2. Okay, got that part. All right, and now I look up on my textbook, which I have, and that says K. Let's see what they're saying here. We're going to say KF for freezing. And I look at my textbook, and by the way, this is on page 553. There's a table that has this stuff on it. All right, I look it up, and I say, you know what? Water, let's see, KF is 1.86. 1.86, and that would be degrees Celsius per little m. All right. So I have my I have my K. Do I have my molality yet? Now the molality part is the part you have to calculate. Okay. All right. So I need, what's molality? Well, I have 351 grams of water, and I've got 49.2 grams of sodium chloride. So I need M. Okay. One, the I just looked at. You just look at the equation. What do you get? I get 2 particles for everyone. The KF, I just looked up. Molality, on the other hand, I have to calculate. So, first thing I need is the molar mass. Remember what I said? Anytime you see grams, you know what you're going to need? You're always going to need a molar mass. And so the molar mass of sodium chloride, I believe, is 55.5 grams per mole. I think it is. This is 23 plus 35.5, 23, 35. That's, well, that's, what is it? Let's see. Let's make sure. Where's my periodic table? So I got 35.5 plus 23. And I can't do the math today. And that is, it's not 35, it's 30, it's 58. There we go. 23 plus 35 is what I get for trying to do it in my head. All right. Always look at the table. So I got 23 for sodium, and I got 35.5 for chlorine. So that is what, 58.5. Okay. So I need that. So let's go ahead and get the 49.2 grams of sodium chloride. Okay. And then we say a mole is 58.5 grams. And of course, it's for sodium chloride. There we go. All right. And so let's go ahead and put that in there. So we go, and it'll be a little less than a mole, 49.2. And then we're going to divide by 58.5. 23 plus 35.5. Yeah. There it is. Yeah. And I get 0.841 mole sodium chloride. Okay. I'm pretty sure I put it in the calculator right. 49.2 divided by 58.5. Okay. So I get 0.841, a little less than a mole. And so a common mistake, though, is to stop right there. And that's a common mistake. Common mistake says, oh, I got the moles. Well, that must be what the freezing point depression is. No, that's not what it is. And it's not the molality either. So now what? That's moles. So what's molality? Molality is what? Moles per kilogram. How many kilograms is that? That's not 351 kilograms. It's 0.351 kilograms. Okay, so now we can divide by kgs. And I have to be careful to put a little space here, because if you put it a little close, sometimes that 1 can look like you're trying to say an L, you know, and sometimes that K can get you confused as well. And so what do we have here? So I'm going to put this in my calculator. I got my 0.841, which I'm leaving in my calculator, so there may be some rounding issues, 0.351. And I get 2.841 2.396 molality. Little m. All right. So it's a fairly robust solution. All right. Make sure I did everything right here. So I got the moles, I have the kilograms, and it's a fair amount. So this is the molality of that solution. Now I can go ahead and say, you know what? It's times 2. There's my I. And then it's times, what's my, what is it, 1.86 degrees Celsius per molal. And look, molals cancel. Okay, and I is dimensionless. You're left with degrees Celsius. And so we can go ahead and put that in our calculator too. So I'm leaving the 2.396 in my calculator. I'm multiplying that times 2 for my I and times 1.86. And I get 8.91 degrees Celsius. Now remember, this is a freezing point depression, so we have to add in a minus onto it. Okay, and so we're going to say, and let's not forget this step here. I know 0, 0, and anything minus from 0 is still that minus number, but let's go ahead and put in that 0 degrees Celsius for pure water. And it seems almost trivial, but if you're not doing water, it's going to have something other than 0, right? Yeah, you got to be careful. Don't get lazy. And so sure enough, the new freezing point of the water is minus 8.91. There it is. Okay. So if you put in that much water and you let it try to freeze, your freezing point won't be at 0 degrees Celsius. It'll be significantly lower. Now that's a lot of salt and a little bit of water. And so we got a fairly large freezing point depression. My point of saying that is that you really need a lot of salt to change the freezing point, and you really need a lot of salt to change the boiling point. Okay. All right. So what if it's going in the other direction? And we'll do a boiling point elevation. And boiling point elevation looks exactly the same, except the sign's the other direction. Boiling point elevation means you're going to add. You're going to add to the boiling point. Okay. So one of the things that I get in class is I'll ask folks, and I'm going to ask you, is why do we add salt to spaghetti water? You know, when you're making spaghetti, usually you throw in a little bit of salt, right? Okay, why do we add salt? And I will get all sorts of answers. I always get all sorts of answers, right? And one of the most common answers I get for why do we add salt to water before we cook our spaghetti is because it'll make the spaghetti cook faster. Because everybody knows that if you add salt, you raise the temperature, right? And I'm like, wait a minute now, how much salt are you adding to this spaghetti water? Just how much? And so let's do that. Okay, so let's say we have, let's see, 2 gallons would be roughly, let's say we have 8.41 liters of water, which is about how much you'd boil spaghetti in, right? And we add, I don't know, a good pinch. What do you think about maybe, let's say a lot of salt. Let's go 5 grams, which is a lot of salt. All right. So we have basically 2 gallons sitting on the stove. And I just took, actually, that's a pretty good handful of salt. 5 grams of salt. It's a fair amount of salt. All right. And maybe about a tablespoon would be 5 grams. That's a lot of salt. All right. And so we add that to it. And I want to see what the new boiling point is, because obviously, if I'm making my spaghetti boil faster, if I'm making my spaghetti cook sooner, then I must change the temperature quite a bit. Everybody agree? I mean, otherwise it wouldn't make any sense, right? So let's figure this out. So what is the new boiling point? All right, first off, the boiling point of water is what? 100.0 degrees Celsius if it's pure. All right, we've already determined that I, in the case of sodium chloride, is 2. All right, and so there's only two things we need to do, and that is we need to look up the boiling point elevation of water. And I looked this up, and I see it's 0.51. And so KB for boiling is, here it is, 0.51 degrees Celsius per mole. The boiling point elevation is actually a smaller number than the freezing point depression. Okay. And so we're going to get 0.5 degree Celsius for every mole of salt that we have in there. All right. And so now what do we need to do is calculate what is M. So what is M? Well, little m is moles per kilogram. And so we got to figure out how many moles 5 grams is. So it's moles per kilogram. And so how many moles do we have? We have 5.00 grams sodium chloride. And a mole of that is what? 58.5 grams, if memory serves me correctly from the previous page. 23 plus 35, yep, that's 58. And so what do we got here? It looks like about 1/10 of a mole. So we got 5 divided by 58.5, and I get 0.08547 mole sodium chloride. Now we should be able to figure out, what's the moles here. And so we've got the same 0.08547 moles, and we need to divide by the number of kilograms. How many kilograms do we have here? Well, y'all should remember this, but the density of water is 1.00 grams per milliliter if it's pure. And so that's, and since that's a liter, that means you have 1,000 grams. All right, 1,000 grams. So that would be 8,410 grams. Okay, and that's because, I took density. All right, and so 84, water's heavy, right? And so that's that many grams, which means it is 8.410 kilograms. There it is. All right, and we put that in there. All right, so we go from 8,400, kind of like a roundabout sort of way, 8,400 grams, because but that's 8.4 kilograms is what that's going to be. And so we take the number that's still in my calculator, and I'm going to divide by 8.410, and I get a very puny moles, 0.081016 little m. Not to be not very surprising. You have 5 grams, had less than 1/10 of moles, and then you got it dissolved in a lot of water. And so we're going to say times 2. There's my Van Hoff factor, because, well, you get a sodium plus and a chloride minus, and times 0.51 degrees Celsius per mole. And I'm just going to leave my number in the calculator, times 2 times 0.51, and I get an astonishing boiling point elevation of 0.01, and there's no point in even adding the rest of it, but I will, 0.104 degrees Celsius. So what's our new boiling point? Well, you add that in, it's 100.0104 degrees Celsius, if you want to go out that far. Basically, have you really changed the boiling point of the water? I mean, that's the whole point of this exercise here. I only added 5 grams of sodium chloride to my boiling water. Did I really change it? And the answer is no, I didn't. I didn't change it. So what's the point of adding salt to spaghetti water? Well, first off, if anybody asks you, and you should tell them very quickly, you'll say, I know the answer. The point is that it's not going to make it cook faster. And of course, you'll never get invited to that party either, ever again. But, the truth of the matter is, if you go from 100.0 to 100.01, you haven't really changed anything, have you? And so why do you put salt in spaghetti water? Well, I'll tell you, it's like the whole shaking the can thing. Sometimes the answer doesn't require a lot of science. It's because it tastes better. That's why. That's why you put salt in spaghetti water, because then, and I always throw in a little bit of olive oil as well for my spaghetti water, when I'm cooking it. And it's because it tastes better. You're definitely not making it cook faster. Okay. Now, we were very careful here, though, when we did this calculation. What was I careful about here? Do you see that? Look there. What do you see? Even though I know it's positive, I went ahead and put a plus on it anyway, because it's a boiling point elevation. I've got to remember that whatever happens here, this right here better be greater than 100, because that's what it means to be an elevation, all right? It better be greater than 100. Now, it's not much greater than 100, but it is a little greater than 100. Okay. Now, what would you have to do to really raise the temperature of that boiling water? You'd have to add a boatload of salt to it. In other words, you'd have to be just, take your salt and just pour and pour and pour and pour. And then it's not so good. Everybody's going to say, what happened to your spaghetti? It's pretty salty today. That's what they're going to say. Okay. And you would say to them, but I wanted to cook a little faster. How much salt did you have to add? A lot. Okay, a lot. All right, so it is 10:54. Believe it or not, we're almost done here. So what I'm going to do, I'm going to turn off the recorder, and we're going to take a short break.